Hi, welcome to the problem session for Lecture 6. This lecture covers max optimization problems, and we're going to do a few examples of those here. Okay. The first one, we're going to be trying to maximize, or rather, find the optima of the function x squared minus x plus 1 in the domain 0 to 1. So, I'm going to go through the whole method step by step. So, first step, we compute the derivative. That's 2x minus 1 using the rules of differentiation we did previously. Okay. Step 2, we're going to solve that equation, that first order condition, like so, which implies 2x star minus 1 equals 0, or x star equals 1/2. So, that's step 2. Step 3, we're going to compute the second derivative evaluated at that point. Well, the second derivative is just 2 at all points. So this is a globally convex function. This is greater than 0 at all points. Therefore, we know that we have a local minimum of the function. So that's step 4 in there. Step 5, we're going to evaluate the function at both this local minimum and also at the endpoints and compare. So the function evaluated at this point is 1/4 minus 1/2 plus 1 equals 3/4. And the function evaluated at 0 equals 1, and the function evaluated at 1 equals 1. So, to conclude, we have one global minimum. So x star equals 1/2 is the global minimum. And then x equals 0 and 1 are both global maxima. That's it. So that's one example. Let's do another example. Here we have 1/3 x cubed minus x squared minus 3x minus 1. Okay. Let's take some derivatives. Step 1, take the derivative. We pull the 3 down over here. Multiply that by 1/3. You get 1. So that's an x squared minus 2x minus 3. We're going to set that equal to 0 to get our first order condition, which states that x squared minus 2x minus 3, let's restart here, equals 0. That's a factor. See if that works. X minus 3, x plus 1 works. And if you're not getting it immediately, just pause here, see if you can figure out how to get that. Note, because there's 3 at the end here, you're going to be using 3 times 1 or 1 times 3. There's already chances of this factoring. So, in general, you can't expect it to factor, but when it's a set up problem for a course video, it's more likely to factor than normal. So there's the factor. That means there are 2 solutions to this equation: x star equals 3 and x star equals -1. Okay, so we have 2 possible, so 2 critical points here, and 2 possible minima or maxima. Okay. Next step, we take the second derivative. That's 2x minus 2. Now this one is not always positive at all x's. We have to actually go through and figure out at each critical point. So this thing is going to be greater than 0 at x star equals 3, and less than 0 at x star equal -1. So this is going to be a local minimum, and this is a local maximum. Okay, what do we do with that? Well, we also have to compute the value of the function at these points and also at the endpoints. F of 3 is going to equal 9 minus 9 minus 9 minus 1 is -10. F of -1 is going to equal -1/3 minus 1 plus 3 minus 1 equals 2/3. Okay. Continue with the endpoints. Oh, I didn't mention the endpoints up there. Sorry. So This is on the domain -5 to 5. So we do the endpoints, -5. That equals -125 over 3 minus 25 plus 15 minus 1 equals -522 over 3. And then f of 5 is going to equal 125 over 3 minus 25 minus 15 minus 1 equals 2/3. So, what do we have here? We have the global minimum is -5, because -522 over 3 is way smaller than -10. So this is the global minimum. This 10 is just a local minimum. -10. So 3 is a local minimum only. -5 is a global minimum. And f evaluated at 5 is the exact same as f evaluated at -1. So -1 and 5 are both global maxima on this domain. Of course, if you change domains, you get different maximum minimum potentially, but in this case, that is you have, in this case, -1 and 5 have the same value of f, and therefore they're both global maxima. There you go. Examples tend to be just like this. You follow the steps, take the derivatives, set to make it to 0 to get your first order conditions, do your second order condition to check to see if you have a minimum or maxima, plug in values at the critical points and also at the endpoints, compare, and you're done. That's it. Thank you very much. And that completes the calculus part of this one-dimensional calculus part of this problem sessions. Thank you very much.